So welcome everyone to this week's Autonomy Talk. This week is a great pleasure to have with us Professor Michael Posa, who is an assistant professor in mechanical engineering and applied mechanics at the University of Pennsylvania, where he leads the Dynamic Autonomy and Intelligent Robotics Lab, which is a group within the GRASP laboratory. Now, something about Michael: he first obtained his Bachelor of Science in Mechanical Engineering from Stanford, and then he worked for a while at a company called Vecna Robotics in Cambridge, Massachusetts, where he was designing control algorithms for the Bear humanoid robot. He then started and completed his PhD in electrical engineering and computer science from MIT, and then joined UPenn. Also, during his PhD, he worked on the DARPA Robotics Challenge. Now, his group focuses on developing computationally tractable algorithms for robots to operate both dynamically and safely while maneuvering and interacting with environments. And typical applications of his work include leg locomotion and manipulation. He has received a number of Best Paper Awards and faculty awards for his work. And the title of today's talk is Multi-Contact Learning and Real-Time Control. This is a very exciting topic, and therefore I'm very happy to hear more and give you the stage, Michael. Go ahead.
Thank you, Julie, and thank you for the invitation to speak here as well. I've really enjoyed following the seminar series, and I think it's a fantastic thing you're doing here. So I want to talk about some of the latest work out of my lab. Most of this has really been done over the last 2 years or so. Throughout the talk, I know we're on Zoom, but feel free to ask any questions. I'm going to open up the chat here just so I can keep an eye on it. But if you want to interrupt and ask a question, I'm happy to take questions throughout, or we can save them to the end. Okay, so we've seen really cool stuff in the world of robotics lately. The video from Boston Dynamics just recently released. So we could also think about exciting results from, let's say, deep learning on the manipulation side. At the same time, despite how impressive these videos are, and I think we can really say that without taking anything away from them, we're still not seeing robots with anything near this level of capability in the home, in the workplace, or deployed. And I think it's important for us as roboticists to ask why, right? What is holding it back? Is it really just a matter of engineering and a little bit more time? Or is there something more fundamental that we as researchers are going to need to address? And if you take a look at these approaches, I think there's a couple of sort of key things here. That are maybe preventing us from taking these robots into the home, into the workspace. And I think a big thing there is the environments that we're expecting robots to deal with in the wild look quite a bit different from those in the videos. You can talk, listen to the folks at Boston Dynamics talk, and it's clear how much engineering effort and how much engineering expertise has gone into producing these results. Right? These are very carefully designed policies and controllers. They're very thoroughly experimented on, in this laboratory setting. There's a lot of engineering expertise that went into this. On the sort of the OpenAI deep learning version, tons and tons of data went into the sim-to-real transfer. And in fact, right, as we all probably know, not too long after the Rubik's Cube work, right, OpenAI essentially shut down their robotics group, claiming that there simply wasn't enough data in robotics to make the sort of progress on deep RL that they wanted to make. There, obviously, OpenAI is still in the news, right? There's something perhaps about chatbots, partially functional as they may be, that's a little bit easier than a robotics in the wild setting. So we have to ask ourselves why. So my lab right now is really focused on sort of one overarching principle, and that's we would like a robot to go into one of these cluttered, nasty environments, let's say into your home, into your kitchen, or perhaps a workplace environment. And we'd like that robot to be able to make useful progress on a task that it's not seen before. And we'd like that robot to do so within a few minutes. So the robot should be able to enter this cluttered kitchen, take, let's say, 30 seconds, 10 seconds, a couple of minutes, explore, learn what it needs to learn about its environment, and then have enough information, have enough skill to accomplish a task, whether that's cleaning or assembly or some sort of manufacturing job. And so to get to that level of extreme data efficiency, it sort of precludes things like very carefully hand-engineered approaches, or precludes things like large-scale sim-to-real transfer, where you're able to spend days or hours ahead of time in simulation pre-training and approach. We really are going to have to adapt to the environment as it comes. All right. Towards this goal, and I'm going to be honest, we're not going to get there today, right? Robotics is still not solved, but towards this goal, I want to think about a pretty classical control paradigm that's used, broadly, I would say, across robotics, and it looks something like this. Okay, there's lots of variations within this broad class of approach, but on some level, you have some kind of task or some objective that's being given to you. You have some kind of slow rates planner involved. Often it works on some kind of simple model, perhaps. That simple model planner produces some lower level targets that are then tracked by some kind of model-based controller, maybe some MPC controller. Okay, maybe your controller doesn't look exactly like this, but probably there's bits and pieces of this structure that are going to look familiar to whatever you're running right now. Okay, traditionally, what this might look like, for it to be a little more specific, is our simple model planner might be doing something like selecting from a few possible contact modes. Maybe it's left-right walking, or maybe it's move to grasp, and so on. And then our task-based MPC is often based around linearization. So the local model there is a local linear model, perhaps time varying, perhaps not. And that MPC problem then is a quadratic program of some sort. And I think this is sort of often where we're at right now in robotics. Once we start moving now to, let's say, dexterous manipulation or cluttered scenes, the interaction between the robot and its environments can become critical. And so I'd really like to, we're going to sort of take a pass at this problem in a few different ways. We're going to start by talking about the MPC block and asking, what happens if we want to do MPC for a robot that's going to make and break contact with our environment? I want to do MPC, except the contact configuration is expected to change, perhaps due to disturbance. It bumps me. I need to reach out and adaptively touch something. Perhaps I need to adjust my grip on an object. How do I do that within an MPC framework? I want to talk about where these models come from, sort of as part 2 of the talk. So where, both the simple and local model, how do we build these from data for environments we've not seen before? So how do we do system identification or model learning? And then we'll conclude focusing really on sort of the simple aspect here, which is I have a very complicated world. There's lots of stuff in it. Not all that stuff is relevant. How do I distill down a simple representation, which is going to enable this pipeline? And if you think about why this framework works, it works because the left-hand side can be run quickly enough in sort of at a global level, and the right-hand side can be run quickly enough at a local level. Okay. To do this, right, focusing now on the MPC aspect, which is where we're going to start, we need a local model. Okay, and where do these local models come from? The normal thing in control design here is to use linearization. And immediately we sort of run into a problem. If I want my local controller to react to things like stick-slip transitions, to be able to move its fingers adaptively, making and breaking contact with an object, linearization is simply not sufficient. Right? Linearization can really only approximate one contact mode. Linearization of one mode tells you literally nothing about breaking contact or frictional effects. Okay, so we're requiring multimodality at some very basic level here. All right, so there's lots of things you could do. The approach that we've really heavily leveraged, and I'll talk about this throughout the talk today, is this idea of a linear complementarity system. A linear complementarity system is really just a rephrasing of a piecewise affine set of dynamics. So we have a set of polytopes covering a space, and in each polytope, we have a set of linear dynamics. You can think of those polytopes as essentially corresponding to contact modes. And this is essentially, and I'm going to do this with a little bit of hand waving here, this is a linearization of all the possible contact configurations in a neighborhood of some particular state. Another way to think about this is we're taking the nonlinear dynamics, the nonlinear, non-smooth dynamics, for instance, the ones you might use in a simulator, and we're linearizing the bits that can be linearized. So we're linearizing things like the smooth forces, Coriolis, gravity, etc., mass matrix. We're linearizing things like geometry, which can be, again, linearized. And we're leaving the non-smoothness. We're leaving the multimodality of the problem, which is embedded via this complementarity constraints. If you haven't seen complementarity before, I don't want to spend too much time diving into the mathematical nuts and bolts of this. This essentially is a quadratic constraint, this orthogonality constraint here, which says that lambda on the left can only be non-zero if the stuff on the right is actually equal to 0. And the easiest way to see that, in the classical sense, and this is what underpins all of our favorite simulators, whether that's Drake or Majoko or Gazebo, all has this sort of core principle under the hood, solved perhaps via different mechanisms with the same principle, where we might say something like, well, let's suppose phi is now the distance between the robot and an object in its environment. The force now can only be non-zero if that distance is zero. So only can be you can only have force when you're touching. Right? This is a way to encode multimodality via a non-convex constraint. And the LCS is just a linearization of this, or a piecewise linearization of this. So let's take this as our model for now. And now let's say we want to do real-time feedback, right? This is our NPC problem. And before I start this, for the next, let's say 10, 15 minutes or so, I'm going to talk a lot about the work that Alp Identically has been doing in my group. Alp is a PhD student who's going to graduate in the next 6 months or so, currently looking for postdoc positions. Alp's fantastic, highly recommend you take a look. Okay, so our NPC problem here. It looks a lot like your traditional NPC with linear dynamics, except we've added in the stuff in blue. And the stuff in blue is corresponding to the multimodality. Right? This is how the contact force and the multimodality enters our problem. This, as it's written down, is a quadratically constrained QP. So it's a non-convex optimization problem. Equivalently, we could write this down via mixed integer programming as a mixed integer QP. Right? These are sort of equivalent. Neither of these are particularly tractable forms where we could solve. Right. So this is a NP hard problem. This is a non-convex problem. And right off the bat, if you've experimented with optimization problems like this, we know for reasonably scaled problems, this is simply not going to be solvable in real time, optimally. And so we have to accept the fact that we're going to move to some kind of suboptimal solution here, some kind of approximately optimal solution. And once we do so, I think it's really important to kind of put a stake in the ground and say, what do I want out of my approximately optimal or suboptimal approach? Because any one of us could write down a set of heuristics right now and a set of some algorithm that's going to approximately solve this, and that's going to have some properties. And yeah, it could be really fast, but who knows if it's good or not? Right. So what do I mean by good here? Right. In the realm of nonlinear programming. And I think there's a few sort of criteria you have to have here. So one is you need an algorithm that's going to be able to explore potential modes. Right. I would like my NPC algorithm to reactively adapt to changing content configurations, to be able to decide that it needs to reach out and touch something proactively in order to accomplish its goal. So it needs to explore multimodality. In order to understand the benefit of making contact, of reaching out and touching something, of, let's say, if you can see my screen, moving your fingers, right, to finger gate an object. If you want to understand the benefit of doing so, well, your prediction horizon has to be pretty substantial. It has to see far enough into the future where you actually can tell, yes, if I pick my finger up and I move it and then I push, I actually make progress towards the goal, which is maybe moving the object, right? So things like myopic or single step or instantaneous optimization problems are not going to be sufficient here. We really do need a prediction horizon. And then lastly, I think, as I've said a few times, we actually need to solve this at real-time rates. Real-time rates being tens of hertz at a minimum here for an online controller. Before I go into exactly this approach, I'll give one quick example here in simulation. So this is a same-level Franca robot rolling two balls. We've given it the objective of moving the balls over to the left. It's given a little bit of guidance as well that the manipulator should be roughly positioned kind of behind the balls. But otherwise, the choice about what to touch, when to touch, and where is made entirely online via the MPC algorithm. Here it's deciding to push the back ball in a way that also nudges the first one forward. Right? It's reasoning about all these possible contact interactions. And then at the end of the clip, I've sort of cut the middle of it out because it's a little less interesting. At the end of the clip, you're seeing that the manipulator going back and forth now between the two balls as it realizes they're sort of side by side, and it's going to have to trade off going back and forth in order to continue making progress towards the goal. Again, so very minimal guidance here given. The contact choices are being made by the robot. Okay. So in the process of this work, and I'll take a quick second and give a little bit of timeline here. So this is a problem that I've been personally thinking about since really year 2 of my PhD. So that's going back 9 years, almost 10 years ago. I've been thinking about this problem, and it's vexed me It's vexed a number of students who've worked in my lab since then. And this work by Alp was really the first time we made progress. So I'm super excited by the progress in this space. Along the way, we've tried other things, and I want to sort of give a brief kind of discussion of other things you might consider as solutions here. So you might want to just write down this as an MIQP, right? Do mixed integer optimization. For instance, you could use a big M MI mixed integer programming problem here to represent these complementarity constraints. You could also try semi-definite relaxations of the non-convex quadratic constraint. And both of these approaches sort of run into the same problems. The most critical problem here is that the convex relaxation at the core of, let's say, the big M version is non-informative. So if you take the convex relaxation, it essentially says, take your integer variable, right, and make it continuous between 0 and 1. What that means for these multi-contact problems is that when that integer constraint is relaxed, you can exert almost arbitrary, half of big M, forces at almost arbitrary distances, again, half of big M. So whatever your big M is, you can basically say, my max force that I could ever expect to exert, I'm allowed to pretend I can exert that at the half of the max distance, right, that I could ever possibly see. And that is simply just not a useful relaxation, right? That tells you really nothing about the multimodality. You're just basically allowed to apply forces willy-nilly across the environment. So these approaches tend to be very slow. They rely on these convex relaxations being useful, and they're not in this case. You might also try something with a differentiable simulator, a differentiable contact model. And this is something that's gotten a lot of, we've seen a lot of progress in this area lately. So some kind of differential simulator, and then apply some sort of gradient-based optimization formulation to this problem. This shows a lot of promise. There's been some exciting results here, for instance, out of Zach Manchester's group at CMU. I think there's a lot still to be explored here. I think the one reason we're not really looking at this is this approach fundamentally now is going to intertwine how soft you make your model, okay, so how differentiable you make it, with its ability to do mode exploration, right? So the softer you make it, the more you can, more your optimization algorithm can uncover potential contact modes, but at the same time, you're giving up physical accuracy there. So what we've gone to instead is an ADMM-based approach. It's also ultimately going to be a local algorithm, right? There's no sort of avoiding the locality here. We're solving, again, this non-convex problem, but it's shown a lot of nice properties. And if you've seen ADMM before, it works by essentially splitting the constraint set. So we're going to take our constraint set and we're going to split it, and we're going to try to split it as intelligently as possible. So in our first stage, we're going to just solve a QP that ignores the complementarity, so ignores the non-smoothness of the problem. Right, this is our favorite. This will look a lot like any kind of QP from an MPC problem, pretty tractable at these timescales. And then the second stage, we're going to solve without the dynamics constraints, only including the complementarity constraints. So taking these two rows, basically, and treating them one at a time. This is the hard part of the problem. This is the non-convex part of the problem. But the beauty of this is that this constraint, this complementarity constraint, only depends on the variables from the ith time step. So dynamics couples things through time, and the complementarity is decoupled in time. And because it's decoupled, we can actually solve the second stage in parallel via n, where n is our prediction horizon, and independent subproblems. Right? These end up being projections. But by splitting this and solving them via consensus formulation, we take the hard part of the problem, we drastically cut down on its complexity, and we can then solve these projections via MIQPs or heuristics. We've explored both of these. And it turns out you can do this for types of problems like the Franca arm I was showing before, at the 50 hertz rate. I'll show a few examples that aren't in sim now. So this is one first example. This is a cart-pull robot that we built in the lab a couple of years ago. So it's a traditional cart pull, except we've stuck on a couple of big foam walls that it can slam into. And a controller really has to reason about these walls if it wants to stabilize the system. If you ignore the walls and just pretend you're linear, you're going to fall over pretty quickly. Because this problem is simple enough, we actually go back post hoc and we can solve the true non-convex optimization problem. And we can compare the result we get with the one we get from our ADMM algorithm, which we've called consensus complementarity controller C3. And it turns out for this problem, we're basically optimal. Okay, so yes, we're running this local algorithm, but it's accomplishing, it's achieving a cost that's almost exactly the same. This is comparing the blue and the red lines on this curve, almost exactly the same as the true optimal solution, which I think is a nice sanity check, right? This problem is not terribly hard. It's only 2 contacts, but we are getting back to the optimal solution. I'll give a few other examples. These are all relatively recent results done over the summer, thanks to Alp and also to Adam Way, who's a summer research student in my lab. I haven't published this yet, but hopefully it should be coming out in the next couple of weeks or so. So here we're looking again at this Franco robot, which has the task of moving these balls around. I've sped up these videos a little bit just so you get a full scope of the motions involved. But this robot is, adaptively deciding where to touch the ball. It's adaptively deciding, yes, if it wants to keep rolling the ball, it's going to need to let go and go back to the other side and keep pushing it. It handles disturbances, which perturb the mode and perturb the sequence, and does so all in real time. So I'm super excited by this work, and keep an eye out for the latest results. Okay, so I want to transition now to the second part of the talk. Again, if there are any questions, feel free to put up a hand or unmute yourself or type in chat, whatever feels good to you. All right, so we focus on the first part on this MPC block here on the right, upper right, and I want to talk about modeling. Where do models come from? Maybe 5 years ago we would have called this SID. Now we call it model learning. Where do these models come from? How do we learn them quickly in realistic timeframes? So the type of problem I want to focus on looks something like this. I'm given some data, some trajectory of a system through space, and this is just here an SE3 pose being plotted. And I'd like to understand the model that came out of that sort of generated this motion. Okay, so this is the kind of data we'll collect and we'll put in a motion. All of us here hopefully can look at this and have some intuition of what's happening, maybe imperfect, but we can tell that there's a couple of bounces in here. Something hit something else, bounced maybe 1, 2, who knows how many times, and then it kind of looks like it sort of skids to a stop at the end. Okay? Don't quite know what object this was. I don't quite know what it was hitting, but there's some couple impacts in here. Kind of looks like it hit something flat. Maybe the details are not totally clear, but the big picture is. Let's take, for now, even a simpler example here, this strobe portrait shown on the slide. And I think we all know what this is. This is a bouncing ball, and it's bouncing on a flat or flat-ish surface, and it has some coefficient of restitution. Right? We all have pretty clear intuition. Right? I want to see sort of how that intuition fits into model learning now, and suppose we have a function f parameterized by theta that we're trying to learn or trying to identify. Right? So what is the function here, which basically maps one state to the next state in this sequence? Okay, so this dot to the next dot afterwards. Okay. It turns out that function is not particularly nice, right? Here I've discretized the time, but if you think about, again, in discrete time, mapping position q and velocity v to the next velocity, you have this big step effect, which corresponds to that impact event. So states which don't hit the ground are the ones down here in blue, and you have this really sharp, nearly discontinuous event here, and then you have the impact event, the ones that are going to hit the ground shown in red. This is not a particularly nice function, but at the same time, deep network, suppose we try to learn f theta via deep network, is biased towards simplicity. It's biased towards smoothness, it's biased towards low Lipschitz constants. And this bias is fundamentally misaligned with the type of motion we're seeing. This is not a hard problem for us to solve, but it's a shockingly difficult problem for something like a deep network. All right, so I'm going to argue for the next 5 minutes or so that unstructured approaches to this model identification problem are doomed to data efficiency or failure at worst. Data efficiency at best, let's say failure at worst. I'm going to give a few different arguments. So that last slide was sort of the, maybe an intuitive argument. Here's an empirical version of that problem. So we took, in this case, a simulator, in this case, Majoka, and we simulated a cube rolling on the ground. And we did this at a few different stiffness levels. So we have a sort of a soft, medium, and a firm version here. The one in the video is the medium. So you can tell even the medium, it's a little softish, not quite what a real cube would look like rolling on the ground. Made this learning problem as easy as possible. And they also wanted to see how stiffness is going to transfer to the learning problem. And there's a few ways we could look at the test performance. So one is we could look at an oracle loss. And this is not something we can do anything about. We have a little bit of noise injected into our data set. Even with the true model, even with the oracle, the hard version, all right, or the firm version is going to have larger error. Right? This is coming from the simple fact that the stiff dynamical system is going to create some chaos. Okay, this is unavoidable. Can't do anything about this. It turns out this is actually still really hard to train. Even memorizing these data sets, right, with an over-parameterized deep network is shockingly difficult. The optimization problem under the hood for training is very stiff, it's poorly conditioned, and it's hard to get it to work. Right? So Mihir Parmar, who's a master's student, and Matt Holm, a PhD student, spent a good amount of time, lots of money on cloud computing on trying to optimize, in this case, a recursive neural network to train these things. We had a little more success with an RNN than something not recursive. And it turns out getting the hard version to train effectively, even in the large data regime, really was difficult. Okay, so there's a problem in training. There's also a problem in generalization. So comparing test loss to training loss. What's happening here at a fundamental level is that the stiffness, again, is conflicting with these biases in inductive bias inside your learning network. So even again, as the number of training tosses goes up, here getting into the thousands, we see that the generalization error remains stubbornly high for the stiff model. So my takeaway from this work was, if we're doing deep learning in sim, we can make the sim softer, right? We can make it more differentiable, to use some scare quotes, more differentiable, and learning is going to go better. It's going to be easier. It's going to generalize better. It's going to work better. But if we want our simulator to reflect reality, and if reality is stiff, we may be getting a false sense of security from this process, right? These problems get artificially easy in a soft sim. Right. One more sort of third take, right, at the same argument here. This is coming from work done by David Bianchini, collaborating with Matney as well here at Penn, looking at what we can sort of prove about generalization in this case. So there's some nice results about generalization in learning, which say essentially that we can bound generalization error, generalization loss, by a term that scales with the amount of data. So as data goes up, this term goes down, and also scales with the Lipschitz constant of the loss with respect to our parameterization. So how does this look like? What does this look like if we take our favorite loss, which is something like a prediction error term? So take the data, xi prime, compare that with our prediction, and then sum and square. So I'll take a toy problem here. This is a ball. It's being dropped. It's going to hit the ground at some height, zg, and all we want to do here is learn the height of the ground. Okay, this ball is going to drop. It's going to hit the ground. It's going to stop. The easiest problem we can imagine, right? This is the toy problem in context. And we want to learn the height of the ground, so we have a single parameter we want to learn. I can write down the dynamics here, and I'll write it down with this max function, which is describing the non-smoothness. We have two versions here. One is no contact, the other is contact. And the dynamics now are quite stiff. They're stiff with this 1 over dt, which is coming from our impact event, so our time discretization of the impact event. And so inevitably here, because the dynamics are stiff, because f is stiff, the Lipschitz constant of the loss is also stiff. And this is simply a fundamental property of trying to deal with stiff dynamical systems. It doesn't matter how we parameterize f. We could have a perfect single parameter version like here. We could use a deep network. We could have a differentiable simulator. It doesn't matter what our parameterization is. This fundamental property remains. If our dynamics are stiff, our loss function is going to be stiff. Our generalization error is going to be poor, at least in its upper bound. So I'm going to argue that this prediction loss is not the right loss. If we want to do model learning, and we want to do model learning for multi-contact robotics, we shouldn't be simulating a model and comparing it with data. There are more clever things we can do. And one intuitive argument for this is to look at graph distance as sort of an ideal loss. So graph distance are errors in variables, which is to say, rather than comparing a sample to the prediction, here I'm looking at some noisy samples drawn from some true underlying distribution in blue. Even though the sample was drawn from this true system, it looks like it's a poor match, right? And this error in pink is quite large. It looks like it's a poor fit to the data. And that's because really what happened is there was a little bit of noise in the X, right, direction. We had a little bit of noise in the input. And so we'd like something like errors in variables, or we'd like something like graph distance as a loss that's going to better match our non-smooth data. Okay. I'll note, graph distance and prediction error are the same up to a Lipschitz constant, but that Lipschitz constant here again is quite high, right? And we'd like to avoid sensitivity to it. Right? The problem with graph distance, of course, is that it's not tractable. Right? This inner optimization problem, min delta x, not particularly tractable. We're not really going to want to solve this in the training process. So what can we do instead? Okay, inspired by graph distance. First, I want to write down an implicit formulation of my model. Here, again, sticking with that toy problem of the ball drop, again, learning the ground height. My implicit formulation is going to say, my dynamics update just involves some force lambda, and I'm going to hypothesize lambdas, or say lambda must satisfy this complementarity constraint. So this is a purely implicit formulation. Same equations we saw before, just written down slightly differently. We could write down that same prediction loss before in this terminology. To say our prediction loss involves calculating an optimization over lambda that satisfies complementarity exactly. So this complementarity constraint is going to, in this case, exactly specify lambda. We'll then plug it back into our implicit formulation. We get back the same equation before. Okay. This might look nothing new here, right? Haven't changed anything. This still has all the same problems as before. This is our prediction loss. A very simple tweak now. Okay, shockingly simple tweak. We're going to take that complementarity constraint and turn it into a penalty. Okay. The beauty of this is that for the model learning problem, we're expecting this loss to be quite small. We're expecting very low prediction error and very low complementarity error. So it turns out turning this into a penalty, and this is really, I think, something special about model learning that doesn't apply to, let's say, something like reinforcement learning or even more generic supervised learning, is that this penalty parameter really doesn't matter all that much. We found, orders of magnitude changes really don't affect the solution here. So we take this complementarity violation constraint, we turn it into a soft penalty, and this preserves the true solution, at least in the noiseless case. So if we have, noiseless data, this actually doesn't change the global optima in the same way that, let's say, softening the dynamics would. If you soften the dynamics, you're actually changing the solution. Here, we're not changing the solution. We're still recovering the same stiff solution as before, but we've reshaped the optimization landscape. Right? So this is a reshaping of the optimization problem as opposed to a reshaping of the dynamics, which you might get out of, say, diff-sim. And the loss function, the Lipschitz constant of the loss, actually no longer depends on the stiffness of the dynamics. Right? In the limit as delta t goes to 0, where delta t was our stiffness parameter here, our 1 over dt, it turns out our Lipschitz constant only depends on this choice of epsilon. And again, epsilon doesn't really matter. We don't make it very small in practice. We make it something like 1 or 0.1. Looking at our ball drop example here, here's what that loss actually looks like. So our implicit violation, implicit loss, this is the one in the solid line, looks, frankly, really beautiful. It's not convex. Okay, that would be a little too much to hope for, but it's really nicely shaped. This looks like a landscape we'd like to work with. You compare this with the prediction loss, and it's just horrible, right? This is a zoom in version on the right. it's flat to the left of the optima. It's incredibly stiff, right? Keep an eye on the scale here. It's incredibly stiff on the right side. This is a horrible landscape to optimize over, right? It has this really tiny little narrow valley at the true global optima 0 here. We haven't changed the optima. We've simply reshaped the landscape. What's going on here? Okay, so I'm gonna try to give a little insight as to what's happening here. So there's a couple things we're doing in this learning framework. So first thing we're doing is we're using an implicit representation of the model. Okay, this is also used in diffsim. We're essentially saying something like there are properties of our system which are easier to represent than the dynamics. So the state transitions are stiff and nasty, but there's some properties, things like geometry, things like ground height, that are easier to represent. Okay, these are the physical properties you might learn in a differentiable simulator. And so we have this, we can think of this simulation problem as some optimization problem, right? Optimization of the contact forces, plug it back into your forward dynamics. This is how modern simulators work, just in some form or other. And so what the standard approach here, the prediction loss, basically says is take my data xi hat, feed it through this optimization block in my network, compute the output, compare that output with my measured output, compute a loss, and then backprop through it. Okay, this is our standard approach. What we're doing is we're never going to simulate for training. Okay, yeah, we have this. We can always go back and if you want to do prediction after the fact, we're going to simulate just like diffsim would. But in the process of training, we are never going to simulate. We're never going to solve this optimization over lambda only relying on the current state. We're in fact going to leverage the fact that we've measured the outputs here, right? We've measured the next state. And this is where I think model learning is fundamentally different from other kinds of problems we might care about, right? We actually have observations of this next state. We can plug them back into our training process. We should use them in training, right? This is something we've measured. We should use it in training for something more than just comparison. Okay. Turns out for things like our robotics problems, we can actually relate this loss to graph distance, and we can relate it to graph distance in a way that's independent of the Lipschitz constant. So actually optimizing this loss will actually bound graph distance. We've taken this approach and we've applied it across a number of different domains. So I'll show one here. So this is a problem of essentially piecewise affine regression. Here we've cast it in terms of learning a linear complementarity system. So given a bunch of data, noisy observations of state transitions, we'd like to identify the underlying piecewise dynamics. And to do so, traditional methods use some kind of clustering. They take a look at your data. This is the true data shown on the left, colored by the mode. And they do some kind of clustering where they try to identify the mode a priori, or at least in the first stage. And then in the second stage, they're going to optimize within the mode. The approach we have via this implicit loss can identify the mode and the model simultaneously. So it's going to do solve the classification problem and the linear regression problem simultaneously by solving this implicit loss, which in this case is a quadratic program. This allows us to scale to things like thousands of modes, to scale to extremely stiff multimodal dynamics. It really, frankly, works beautifully for these problems. So if you're thinking about a piecewise affine regression problem, I would strongly suggest taking a look at this work from L40C last year. Again, the loss function here is a QP. We differentiate through the QP, via an implicit learning setup. And you can see on the right the training process as it's simultaneously fitting mode and dynamics in this type problem. Going backwards in time a little bit now. So I've sort of presented this a little out of order chronologically. I'm going to go back to a more physically grounded problem. So here we're trying to learn this motion of a cube. This is actually that IC3 trace I talked about a little while ago. We'd like to learn a predictive model of this cube. If we take data here, so we're using motion capture to understand the pose, and we feed it through a deep network, we get something like the video on the right, which says, my prediction kind of gets bulk motion correct. Here trained on hundreds of tosses, but it gets rotation completely wrong. It doesn't understand anything about penetration with the table. It doesn't come to rest in the right spot. It looks kind of right, but really wrong in some important qualitative ways. Okay. With this same idea here, this implicit learning approach, we can do much better, right? To say shortly. So if I think about how a simulator works, shown here on the left, simulator right now is going to basically compute a couple different things. It's going to compute some geometry terms, let's say sine distance functions and maybe frictional Jacobians. It's also going to compute things like smooth forces, Coriolis forces, etc. It's going to take those two things. It's going to plug them into some contact force solver. This is where all the magic is in your simulator. This is the non-convex hard part of the problem. And it's going to come up with a force. Okay. So what we're going to do is we're going to learn those smooth bits. This is the implicit representation. So we're going to learn smooth forces, and we're going to learn geometry. But instead of plugging them into a solver for training, we're going to plug them into this implicit loss function. Okay. Again, for simulation, yes, we do the contact force solver. In fact, we can take what we learn, we can plug them into your favorite sim. We've actually integrated this into Drake, for example. So we can take the stuff we learn and simulate it via Drake. But for training, we're going to put this into this physics penalized implicit loss. The results here are super exciting. So in a handful of tosses, 5, 10 tosses, we ran this actually demo live at ICRA this last year in 2022. So actually we're learning the model with real-time observers in a couple of minutes. With a handful of tosses that identifies geometry, identifies friction, identifies mass in a way that's far more accurate than anything on structure. We can figure out geometry extremely quickly. It depends a little bit on how much structure we give the problem. So this is actually unpublished as well, very relatively recent results here, showing that we really don't need a lot of structure here. So here we're actually learning a deep neural network that represents geometry here via support function. And even with this deep neural network, this is the demo we ran in ICRA, it takes only a minute or two of data to identify the actual system. We take this cube, we toss it about 30 times, and it can fit this deep network to identify, yes, in fact, it was a cube. And in fact, it's a pretty sharp cube, sharp corner cube. All right, I want to conclude now the talk with one more section here, thinking about simple model planning, right? So we have two pieces right now, which I think are nice. We've made a lot of progress on control, real-time control, although limited somewhat to fairly simple examples. Okay, I think honestly, a robot arm and two objects seems pretty complicated, but the objects are spheres, so there's still a little bit of a gap between that and my real-world kitchen. We've also talked about how we can learn models from data. So I'd like to sort of think about how do we get to that complex environment? And the key missing feature here is we need to distill something simpler for the control block. All right, we can't do real-time control on the kitchen, right? We need a simple representation that's going to be useful. And a simple representation is inherently now going to be tied to our task, right? One simple model is going to be useful for one set of tasks, another simple model might be needed for another set of tasks. So for example, problem here, this is all done in simulation, although we're working hard right now on transferring to the real system. We're still building this tri-fingered. So we have a tri-finger simulation, thanks to the folks at ODRI, where we have 3 fingers, we have a cube. Between the 3 fingers and the 6 faces of the cube, there's thousands of possible modes here, making and breaking context, sticking and sliding. This is still a somewhat simple task, right? This is still not the kitchen, but it's also way too complicated for model-based control. Right? If I wanted to model everything here and do my solid MPC, it's really not going to run in real time. At the same time, if you wanted to throw RL at this problem, it's going to take hours to days of data. Okay. So what's a sort of nice middle ground here where we can get this done with a high degree of accuracy, but only in a couple of minutes? And the key insight we're working on here is that this full complexity is simply not necessary. If I want to solve even a fairly complicated task, even some kind of in-hand dexterous manipulation task, I don't need thousands of modes. I only need a few. And so a controller should be able to be successful while only reasoning over a few possible modes. That's not to say the other modes don't exist. They do exist, but maybe they're not that important. Maybe they're not important because they are very similar to some other nearby mode. And maybe they're not important because the optimal controller is never going to visit them. Or if it does visit them, maybe it's only going to visit them very briefly. So what level of complexity is required, and how can we distill a representation that's going to be effective for control? To do this, we're going to go back now to our LCS representation. So we're going to say we have some true dynamics, some oracle dynamics on the left, which are nonlinear. Maybe they have some nonlinear complementary dynamics. Maybe there's something else, but they have some extremely large number of possible modes. Modes here driven by this capital lambda. We'd like to approximate this with a reduced order LCS. And in a reduced order here, meaning reduction explicitly in the number of modes. So we're going to say the mode count is the thing we really want to drive down, because the mode count is what's determining really the complexity of our control problem. So we'd like to find a low dimension lambda here that approximates this. Our goal here is to minimize the performance loss. So suppose we had the oracle, suppose we could do control for the oracle. We have some kind of best case performance. We'd like to achieve something that's close to that by doing control with my model reduction. All right, this formulation, is not, we can't exactly optimize for this directly. We can't even exactly calculate this because we don't know the oracle necessarily, but we can bound this in a reasonable way by on-policy performance. Okay, so we're going to do something that's very, very simple here. We're going to take our LCS learning algorithm. We're going to learn a model based on some data that we collect. We're going to take that model, we're going to pass it back to our MPC algorithm, which is going to take the LCS, it's going to take some task, it's going to operate on our trust region so it doesn't leave the data set by too far, and then we're just going to repeat this. Okay, so this is basically just on policy model identification with a model-based controller, a form of model-based RL, if you will. Before going back to the trifigure, I want to show the simulated data here. And maybe now is, I guess, a good time to pause and say this work here on control has all been done by Wenqin Jin, who's a postdoc in my lab, currently on the faculty market. So if you like this work, which I think is really great, definitely check out Wenqin. So here's a synthetic data set. We have 100 plus modes in the true data set, and we're going to try to approximate with just 4. So on the left is the closed loop phase portrait. This is a slice of the phase portrait, closed loop phase portrait of the system. You notice because it's closed loop, everything is going now into the origin. It's nice being stabilized here by the true optimal controller. And you can see the different modes colored in the plot. In the middle, we have the learning performance here. So this is the algorithm as it's identifying a model that's appropriate for control of the system, along with the closed loop performance using that particular model. On the right, comparing the two different closed loop behaviors. And what we see, somewhat surprisingly, is we can dramatically cut down on the number of modes here for purely synthetic data, random systems that we've randomly generated. We can dramatically cut down the number of modes by orders of magnitude with paying almost no cost, no cost penalty. The cost goes up by 1-2%, depending on the dimension of the problem. And so we really can get away with running a controller on a far simpler system here, even again for totally random dynamics here. Okay. I'll show this on the trifigure now. So we're learning this trifigure, this 3-fingered manipulation problem. We've given it no prior information about the object. Simply set this up as an RL problem, right? It learns a reward. It learns it's given trajectory data. So. But it does nothing about the geometry of the object or any of its mass or inertial or frictional properties ahead of time. And it can learn to manipulate this cube in under 5 minutes. And by the end of this training process, it's extremely high performance. Let me see, I lost my other videos. It goes back. Okay. This reduced model has something like 30 modes. It's shockingly robust to domain randomization and perturbation. So I apologize for the videos at the bottom are being a little bit cut off. The 3 videos at the bottom are showing performance under perturbations in closed loop, with the right corresponding to really massive unrealistic perturbations. But under more realistic settings, this works shockingly well. Perturbations bump you out of your contact mode. The model and the controller are capable of responding and recovering to these things. So we're, to give a little sort of intuition here, I suppose, we're learning a multimodal model, but we have no real guarantee that this model is going to correspond to true contact modes. We've gone back and looked at the results a little bit and tried to correlate the observed contact configuration with the predicted mode. And there's a pretty reasonable correlation, right? We are learning something about various ways in which you could grasp or manipulate this object, and those are corresponding to different selections of our learn lambda, which again is not a true force, right? It's a purely hypothetical term which generates multimodality for our learn model. What you'll see if you look at these videos, by the way, that we really are leveraging, the multi-contact aspects of this problem. These same fingers do not always touch the same faces of the cube. They in fact are making some decisions about when to make and break contact and where to do so. Okay. So this work, again, all in simulation, recently put up on archive. We're working on transferring this to a real system, but I think it's really showing that how do we bring together these two different aspects of what we've been working on, the ability to do real-time control in this multi-contact domain with the model learning aspects, and I think we're starting to edge closer towards those goals. Okay. Scale this back up. Okay. All right. With that, I'm gonna wrap up and take questions. I think there's a long way to go, right? For till we get to real-time human-like performance. I think the takeaway from today is really that these very quote-unquote standard or very quote-unquote generic hybrid methods are really not well suited to this low data robotics regime. If I want my robot to operate with seconds to minutes of data, it's going to need some structure, right? I don't want to impose too much structure, I lose the power of learning, but I want to impose structure that acknowledges the fact that these problems are in fact discontinuous or non-smooth, and that we need to embed that structure into our problem somehow. Going forward, we're very interested in limiting things like the need for motion capture and better fusing both tactile sensing with motion, with vision, all in this predictive and control framework together. I think these vision and tactile sensing and motion are all very tightly connected by geometry, by dynamics, and we need to leverage that fact. I didn't talk today about any of the locomotion work in the lab, so I'm just going to show these a couple of videos so you see some of the work we're doing there in terms of jumping and handling impacts and leveraging simple models in the realm of locomotion as well. And with that, I want to thank all the students who did the work. A lot of the control work was done by Alp, hiding here in the back. A lot of the work on model learning was done by both Matt Hum and Bibbit, and the work at the end on simple model control was done by Wen Chin. And I'd like to thank our sponsors as well. So this work in particular, NSF, Google for some of the early model learning work, and TRI for a lot of the work on model simplification. And with that, I will happy to take any questions. Thank you all.
Thank you, Michael, for the great talk. A lot of cool insights. Let's open the stage for questions. You can either unmute yourself and raise your hand, and I will call you, or just write in the chat, and I will read the question for you. So let's see who wants to start. Okay, Robert, go ahead.
All right, thank you. Very nice talk. I was particularly intrigued when you were going deeper into the comparison of rigid versus soft contact simulations, particularly the work where you were showing this cube experiment. Could you explain a bit more what the repercussions of that are in terms of, let's say, hand manipulation? So if I'm thinking of setting up a simulator where I would like to pick up objects, and I'm dealing here with a partially rigid, partially soft sort of robotic setup, and I would like to rely on my, let's say, scalable environment, like a differentiable simulator with many of these instances running, but I can actually not trust it very much, particularly if I'm dealing with a very rigid contact. So what would be immediate rescue? Is it basically using your training approach that you were showing afterwards, where you're saying, or what would be the way for us to directly tackle this without becoming extreme specialists on that side of simulation?
Yeah, good question. So I think the big takeaway, I would say, the one sentence takeaway is, if you're going to use differentiable simulation or a smooth simulation, be cognizant of the fact that the problem will be artificially easy if you make it too soft, right? And so you sort of, if you wanted to reflect reality, and in the case of a reality is stiff, suppose you have a soft robot, okay, great, do soft sim. But if the reality is somewhat stiff, you need to address that stiffness somehow, okay? And I'm not saying this is the only approach, right? There's lots of people working on, homotopy-like methods where you start soft and you gradually increase some kind of stiffness parameter and get to stiffness. I think our approach here, I really like it for things like model learning, because it doesn't feel like we have to give anything away. It doesn't feel like we have to make a sacrifice where we say, yeah, we made it a little bit softer, and so it's less realistic, but therefore it's learnable. I think we can sort of have our cake and eat it too with this implicit setup. So that, I'm biased, obviously, right? Use the stuff we're working on, right? But I do think it's a nice approach for these supervised learning problems. Okay, if you're doing RL, it actually doesn't work, right? We don't have that supervision. We don't know the next state, for example, right? And so we can't supervise in the same way. So I think the RL version of this is still very much open question, something we're interested in exploring. But for model learning, I think, I'm biased, obviously, but I'd recommend giving it a try.
Thank you.
Thank you, Robert, for the question. There is another one in the chat, which is from Jung. What is the consequence of enhanced learning in accurate contact dynamics for model-based RL? How does the precious NN-based MBRL seem to have performed well? I think probably it's previous.
Yeah.
Not precious.
Yeah. So if you look at, let's say, the generalization results or the training results, I'm not saying that you can't get generic deep learning to work, but I am going to claim or argue that I think it's going to take a lot of data, right? And I think there's both these empirical and theoretical results, which essentially say the amount of data you need is going to scale with these Lipschitz constants, right? If you don't leverage structure. So if you want to do, let's say, sim to real, and you know your task ahead of time well enough where you can simulate it, and you can spend a day, training your sim to real algorithm, or you have, a couple of $1 million, and you can set up a robot farm here to solve your problem, and you can collect massive amounts of data. I think it's going to work. There's no reason to say it's not going to work, right? It will eventually get there. Right? You'll mitigate that Lipschitz constant factor with data. But I think that it was Terry who asked that question. I'm not aware of anything that looks like model-based RL in this low data regime, right? Talk seconds to minutes of data. So feel free to point out something if you know, but I just don't. I'm not aware of anything that's doing dexterous manipulation in low data.
Okay, Jung. Oh yeah, Jung says thank you. Any other question? I actually was curious about. So I liked when you I think it was marked down the number, like slide 13. Essentially, you described that you brought the constraints into a penalty to make the problem easier to solve, and I was curious about, so did you experience some situations in which it's hard to tune this penalty correctly, or does that simply work every time for your use cases?
I would say it requires a little bit of tuning.
Okay.
But tuning to within 1 or 2 orders of magnitude. We have some results, at least on the synthetic data, in the paper by Wenchen, where we look at sensitivity to that parameter. And in general, there's a very large range. It can't be too small, It can't be too big, but there's a big range, orders of magnitude, where it seems to work pretty well. And maybe just to give a little bit insight as to why this works for model learning and say it doesn't work for control. The key thing here is that this part of the cost here, this prediction error part of the cost, is going to be very small. Right? If you're close to optimal, this is going to be near zero. It's only going to correspond to things like measurement noise and model error. If you want to do something like this for control, let's say, so turn this into an RL framework where this part is now your control cost, that's not necessarily small. Right? It's like your control effort. It's not necessarily small. And so now at that point, you really are weighting the cost you care about with the violation cost. But in the case where both of these are expected to go to something close to zero, you're not actually having to trade one off against the other. They're both going to get small enough across a wide range of steps.
Okay, interesting. Thank you very much. Let's see. Is there any other question from the audience? Doesn't seem so. I mean, I think at some point you left your contact on this slide so that people, I think you can reach out to Michael if you come up with questions while watching the recording or later on.
Definitely.
Thank you very much again, Michael, for the great talk. A lot of cool material. Excited to see what's next.
Thank you very much.
And yes, I will follow up with the recording, what's been edited. Thank you. And thank you all for participating. See you all next week for the next talk.